Okay, continuing on with systems of differential equations. Now, this next set looks almost like the first, except this time around we have in the first equation, we have the subtraction of 5 times x of 2 as opposed to addition of 5 times x of 2. Everything else is the same. And letting A represent the coefficient matrix, again we have 2 and 1, and this time for the second column we have -5 and -2. And we have again the identity matrix, which will consist of 1 and 0 and 0 and 1 as we look at it column by column. And in establishing what we have for the determinant of A minus lambda I, again lambda is in reference to the eigenvalue, and looking at what we're going to have in this case. So if we have for A minus lambda I, okay, we have 2 minus lambda times 1. So we have 2 minus lambda once again, and we have 1 minus lambda times 0, so that's going to be 1, and we have -5 minus 0, so we have -5, and we have -2 minus lambda, and again just taking the diagonals. Okay, so you have again just in correspondence. Okay, so you have first diagonal upper left, lower right, taking the products. Okay, first of all I have 2 minus lambda, quantity times quantity of -2 minus lambda, and we have again with the other diagonal, whereupon we're going to be deducting the product. So we now have minus 1 times -5 is equal to 0, and just taking again what we have now. So we have -4, we have -2 lambda plus 2 lambda, those will go out, and we have plus lambda squared, and we have what's going to be the negative of -5, which would be +5, is equal to 0, and here we have lambda squared plus 1 is equal to 0, and we have that lambda squared is equal to -1, and for what we're going to have in this particular case, now we're going to have that lambda is going to be positive and negative I, and you can have for lambda of 1, you can let that be either I or negative I. We'll just say we have I and the conjugate. You know, we have like a bar that's going to go over lambda of 1, so the bar represents just the conjugate. So we have negative I, and with complex eigenvalues, especially for a two-equation system, we need only one of these eigenvalues to establish the eigenvector. So we need just one eigenvalue, one eigenvector for the system. And now just taking what we have now and going back to what we had earlier. Okay, so you have the matrix A minus lambda times I times the eigenvector is equal to 0. And just to kind of clarify, so you can see we have A minus lambda of 1 times I times the first eigenvector is equal to 0. And again, so we have lambda of 1 equal to I, and we have just taking what we have for the corresponding parts. Okay, so again, so we have 2 minus lambda, so you can see we have 2 minus I, and you have -5 and 1, in the lower right section again have -2 minus lambda, so you can see we have -2 minus I. And for the first eigenvector, again we'll have just the general coefficients. So we have A of 1, B of 1, and for 0, zeros throughout. Now, and looking at writing what we have in the relation between A of 1 and B of 1, and we'll just map together, and we'll say that we have just mapping together. So we'll have 2 minus I quantity times A of 1. We say we have minus 5 times B of 1 is equal to 0. And we'll just say that we have, in this particular case, just for mapping together. So we say we have 2 minus I times A of 1 is equal to 5 times B of 1. Okay, and now for what we have for the first eigenvector, just think of it kind of like this for A of 1 and B of 1. Okay, so we have for the first eigenvector, let me give you just a bit of a visual. We have like 2 minus I times 5 is equal to 5 times quantity of 2 minus I. So we can say that for the coefficients that we have for A of 1 and B of 1. Again, 2 minus I times 5 is the same as 5 times 2 minus I. So we'll say that we have A of 1 is going to be a 5. And we have for B of 1, again, that is going to be a 2 minus I. And again, we need only one eigenvector. So in taking what we have now, so again we have x of t, and we have c times v times e to the lambda of t. And since we're utilizing at this stage, okay, just one eigenvector, one eigenvalue. So we'll have, in this case, right, so we have x of t is equal to c of 1. First eigenvector, again we have 5 and 2 minus I. We have e to the lambda 1 times t, so you have e to the it. And just to show you the direction that we are heading, okay, remember going back to the Euler identity, have like e to the it, and that's going to be equal to the cosine of t plus I sine of t. So we have this particular case, so we have for x of t, so we have c of 1 and times 5, and we have over 2 minus I, and we have upon replacement, okay, so we have e to the it, so we can say we have the cosine of t plus I sine of t. So you're going to have for x of t, so if I just kind of take what we have here, so we have at the top layer, and I'm just going to sort of compile together what we have here. So we have, okay, so we have in this particular case, right, so we have x of 1 of t, and we have is equal to 5c1 cosine of t, and I have plus 5c1i sine of t, and we have for the lower portion, so we have x of 2 of t, and just looking at what we have in the layout, okay, so doing a little bit of foiling, okay, so just working with what we have here, so we have 2c1, so we have cosine of t, and still working with 2, so I have 2c1 times I sine of t, and for the minus I portion, okay, so we have minus c1i cosine of t, and now we have minus c1I times I, and let me mention, okay, so recall now I squared is equal to -1, and we're going to have the negative of I squared, which would be the negative of -1, which would be a +1. Okay, so we're going to have, for this particular case, now we're going to have plus c1 times the sine of t, right? And if we were to follow through and say that if we let c1I be equal to c of 2, we have for the first general solution, okay, so we have 5c1 cosine of t, and we have plus 5c2 sine of t, again, little history repeating, letting c1I be equal to c2, and just gathering, okay, what we have here. Okay, so we have, in essence, okay, so we have just partitioning out, okay, so you have with just our c of 1, okay, so you have 2c1 cosine of t, c1 sine of t, so we say we have c of 1 times the quantity, and just packaging together, so you have 2 cosine of t plus sine of t, and where we had the c1I terms, again letting that be in reference to c of 2, so we can say we have c of 2 times 2 sine of t minus the cosine of t. Now, we'll admit that this is getting a bit crowded, and it's a fortunate thing that we needed only one eigenvalue and one eigenvector for this formation of the general solution. So again, we have for x of 1 of t, we have 5c1 cosine of t plus 5c2 times the sine of t, and again we have with x of 2 of t, again, so we have, so you got c of 1, and just packaging once again, so you have 2 times the cosine of t plus the sine of t, then we have plus c of 2 times the quantity, again 2 sine of t minus the cosine of t, and that is the result.